You're watching a Channel 98 NBISD TV production.
Hey, welcome out there in TV land to Deja Vu, it's Algebra 2. As always, I'm your host, Kevin Corpy. Today I'll be taking you on the extension of the mathematical voyage that we began last week with old Captain Expert. Remember him? Had me tied up, then he realized that he needed me. He couldn't do the math, so he untied me. And when I finally got to the math, we were talking about matrices. Matrices are a hugely important topic. Last week we kind of got our feet wet a little bit. We looked at matrix addition, matrix subtraction, and then we looked at matrix scalar multiplication. That is taking a number and multiplying it by a matrix. Well, today we're going to take it one step further. We're going to look at the operation of matrix multiplication. That is taking one matrix and another matrix and multiplying them together to get a brand new single matrix. Now, it doesn't always work. So by the end of the show, you should know, number one, when does matrix multiplication work? Number two, when it does work, how do you actually do it? And at the end of the show, number three, you're going to figure out, why do we even want to learn this? That's going to keep you hooked for the whole show in memory of Captain Expert. So download those worksheets from the district website, www.newbraunfels.ted.net, and we'll get going. Lesson 9, matrix multiplication. Okay, now remember last week we did look at matrices. We looked at addition, subtraction, and multiplying by a scalar. And a scalar is just a number. It's a constant multiple. We just distribute it to every entry. Today, again, we're going to look at multiplying two matrices together to achieve what's called a matrix product. Product specifically, not just meaning an output, but a output that comes from multiplication. Now, two matrices, column A and B, can be multiplied to get one new matrix, which will be their product AB, only if, that means under these circumstances, in these circumstances only if the number of columns in the first one, A, is equal to the number of rows in the second one. Columns of the first, the one on the left, has to equal the number of rows on the right. Okay, very important. The product of then what we're going to call an m by n dimension matrix with an n by p dimension matrix will end up being an m by p dimension matrix. So notice that these n's are the same variable. N is the number of columns in the first, and that's equal to n, the number of rows in the second one. And those have to be the same in order for the matrix multiplication to work. And our result is going to end up being what's left on the outsides, an m by p. Okay? Now we can identify an m by n matrix, again, that has the letter A, by using a subscript m by n. So we don't have to just say matrix A and then refer to its dimension independently. The subscript, much like we did last week with the address of an entry, will serve two purposes, naming the matrix and giving us the dimension. Okay, let's look at this example right here. I have matrix A and matrix B. Matrix A, remember, is a 2-row by 1, 2, 3 column. So we'll call that a 2 by 3. Rows by columns, rows by columns. And matrix B, I have 1, 2, 3 rows by 1, 2, 3, 4 columns. So it's a 3 by 4. So if I wanted to find the product, A, B, will it work? Well, here's a nice way to figure it out. Write A and B on the left and put their dimension underneath it. So again, I have a 2 by 3 and a 3 by 4. If these inside numbers happen to be the same, that means another number of columns in the first is equal to the number of rows in the second, then the matrix multiplication will work. And our result then is going to be the dimension that's left over on the outside. In this case, it's going to be a 2 by 4. Okay? And so the multiplication itself will work. We're not going to actually do the multiplication in this case. I just want you to know when it'll work. Now that's A times B. Let's come off to the side here. What if I did B times A? Will B times A work? Well, let's see. What's the dimension of B? B was a 3 by 4, and A was a 2 by 3. So just multiplying them in a different order, let's see what happens. Here's the number of columns in the first one. It's 4, and the number of rows in the second is 2. Right there, 4 does not equal 2. So guess what? B times A does not work. Very interesting. It only worked one way. We're going to get back to that very important consequence here in just a little bit. Let's look at another example. Call it matrix P and call it matrix Q. A and B kind of get a little old after a while. Matrix P is a 1, 2, 2, 3 row, 1, 2, 3 row, 3 by 1, 2 column, so it's a 3 by 2. Matrix Q, boy, that's a big one there. Let's see, 1, 2, 3 rows, and let's count the columns. 1, 2, 3, 4, 5 columns, so it's a 3 by 5. So can I multiply P, matrix P, by matrix Q? Well, again, if I write it as a 3 by 2 and a 3 by 5, we'll compare these inside numbers, and a 2 and a 3 are not the same. So matrix PQ does not work. It doesn't exist, or we say that the matrix product is undefined. Okay? Let's see if we worked it the other way. We commuted the two, we say. Q times P. Will that work? Well, matrix Q, remember, was a 3 by 5. Matrix P is a 3 by 2. And once again, the inside numbers there are not the same. 5 does not equal 3, so QP is also undefined. Or we can say DNE, which stands for does not exist. So in this case, it didn't work either way. So there you go. You're already kind of planting the seed in your mind that matrix multiplication, first of all, doesn't always work. And when it does work sometimes, we can't multiply them in any order, like we're used to with numbers. Okay? So now that we know when it'll work, let's go ahead and figure out how we actually find it. And it doesn't really involve a magnifying glass unless your problems are written very, very tiny. And they're probably not going to be. Okay, so how do we do that? Well, let me read this statement here. This is one of those things that's actually easier done than said. So here's what it says. We're going to simply, that's a relative term, we're going to add the products of the consecutive entries of the rows of the first matrix and the columns of the second. We're going to add the products of the rows and columns. Rows times columns, add them up consecutively. Whew, I don't know, Mr. Corpy, that sounds awfully confusing. This one actually is. Let me show you an example, and we'll work it out nice and slowly, and you'll see that really it's just a systematic process that's not too bad. So here we go. We have three matrices, capital W, capital X, capital Y. Capital W is a 3 by 2, X is a 2 by 3, and Y is a 2 by 2. Let's go ahead and write that underneath here. 3 rows, 2 columns, 2 rows, 3 columns, and Y is a square matrix. It's a 2 by 2. We want to find the following matrix products if possible. And if it's not possible, we want to say Y. So let's do W times X. Well, let's come out here to the side and see if it works. W is a 3 by 2, and X is a 2 by 3. So notice we're using very small numbers. Let me zoom in there. Apologize. We're using the X, which is our old multiplication symbol, to denote a dimension, a 3 by 2. Not necessarily multiplication, so be careful there. Now, does this work? Well, notice the insides here are both 2's. The number of columns in the first is equal to the number of rows in the second. So yes, it will work. Now, we also know when it works what the resultant dimension will be. It'll be a 3 by 3. Okay, that's kind of nice so that we know what our answer needs to end up as. Well, let's see how we actually do it then, now that it works. I'm going to go ahead and rewrite my matrices here. We have a 3, 1, 2 in the first column, -2, 0, -1. We have to write W first, and then I'll rewrite X next door to it. 4, 7, -2, and then 5, 1, -1. Okay, so writing them side by side is the first key step. Now what I'm going to do is I'm actually going to work it out. And I'm going to talk you through the process. Okay? Here we go. We're going to take the first row of the first one, and we're going to multiply it by the corresponding entries in the first column. So first row, first column. Let's use a different color for that. Straight across the top and straight down the first column there. And that's going to give us a first row, first column position in our new matrix, or the 1, 1 position. So here's what we do. 3 times 4, and I'll write this out. 3 times 4, that's the 1, 1 times the 1, 1. And then we go across and down. So -2 times 5, and we'll add that, -2 times 5. That is our new 1, 1 position. Okay? Now we'll work all the way across down the other two columns. So I'm going to stay in my top column, first row, but now I'm going to go to the second column. First row, second column, that's going to give me my new 1, 2 position. And we'll do the same thing. 3 times 7 plus -2 times 1. -2, 1. And that's my new first row, second column. And I'll just keep proceeding in the same fashion. I'll do my first row, third column. So I'm going to have 3 times -2, which is, I'll just write it out, 3 times -2, and that is negative. And then I'm going to go -2 times -1, and I'll add it, -2 times -1. So with my first row, I went through each of the column, and I got my new 1, 1, 1, 2, and 1, 3 position. Well, that is a systematic process, and we'll just continue it now for the other rows in the first one. So I'll start with 1, 0, and I'll do the same procedure all the way through here. I'm going to save a little bit of time and multiply them in my head here now, and I'll say it out loud. So I have a 1, 0 times a 4, 5. So 1 times 4 is 4, plus 0 times 5 is 0. That's this column, and then I'll move along. 1, 0 times the second row, second column. That's going to be 7 times 1, plus 0 times 1, which is 0. And then finally, my second row, third column. That's 1 times -2, which is -2, plus 0 times -1, which is 0. All right, and then I am on my last row. So I got a 2, -1, and my 4, 5. So this is my third row, first column. It's my new third row, first column position down here. So I get a 2 times 4, which is 8. -1 times 5 is -5. And then I do it for the second column. 2 times 7, that's 14, -1. And then finally 2 times -2, that's -4, plus 1. And there we go. Now, all I have to do, this is the hard part, staying organized. Now I just go through, and each of these I have to simplify, and I'll get my resultant matrix. So I get a 12 minus 10, which is 2. And then I get a 21 minus 2, which is 19. And I get a -6 minus 3. Well, that's a -6, sorry. -6 plus 2 is going to be a -4. And then down here, since I did a lot of the multiplication together, it's a little bit easier. 4 plus 0, 7 plus 0, -2 plus 0. And finally on the bottom, 8 minus 5 is 3. 14 minus 1 is 13. -4 plus 1 is -3. And there is our resultant matrix. And notice it has 1, 2, 3 rows and 1, 2, 3 columns. So it was, in fact, a 3 by 3, which is what we anticipated it would be in the very beginning. That's a lot of work. We're going to work one more like that. Let me show you, first of all, how to do that operation on the calculator. It's always nice to know how to do it both ways. Okay, here we are. Your calculator can handle matrices, which is the whole point that we're starting them, because they're easy to program with. You have a matrix button on the 83 pluses. It's the second command of the inverse button. And we're going to go ahead and go to Edit, which is clicking to the right, and we're going to edit A. We're going to call it A. Now at the top you have dimensions. It's the 1 by 1 by default. So I'm going to go ahead and type in what W was. It was a 3 by 2. So I hit 3, enter 2. And as you do that, you can see your rows and columns up here kind of forming. Now it's got a darkened spot right here in the 1, 1 position. So let's go ahead and enter it. It's a 3. And if we hit enter, it'll go straight across like we're reading a book. So that was a -2. And then down I get a 1. And then I get a 0. And then finally in the 3, 1 position. And notice it tells you what the address is down here, which is kind of nice. A 2. And then finally in the 3, 2 spot I got a -1. So I have inputted the data now for the first matrix. I'm calling it A, but on the paper I'm calling it W. Not a big deal. Now we need to enter matrix X. So I'm going to hit my matrix button again, and I'm going to go to Edit. I'm going to click down to any matrix I want. I'll call it B. And now I need to type in its dimension. It was a 2 by 3. So 2, enter, 3, enter. And then I'll just type it in from left to right. It was a 4, a 7, and a -2. And then I got a 5, a 1, and a -1. And it's always worth kind of checking again to make sure that everything in here is typed in correctly. Data entry is almost a mind-numbing experience. You just have to be very, very careful. Okay, so now we have both matrices in there. We're going to go to the home screen. We're going to hit second mode, which quits. On the home screen, I can let the calculator do all the hard work for me. I just need to recall now the 2 matrices that I plugged in. So I'm going to go back to my matrix command, and now instead of going to edit, I'm going to recall the first column of names, and the first one there is A, so I'll hit enter, and notice it shows up. You don't have to hit the times button, but it's a good habit to get into. Times, we're multiplying, and we'll hit the matrix command. We'll go down to B now and recall B. And so on your home screen, you should have matrix A, and notice it has it in the brackets, times matrix B, and watch this. Hit enter, and boom. It actually gives it to you right there, which is pretty nice. So you can compare that answer with what you get by hand. But you should know how to do it both ways. Don't ever let the calculator be a substitute for your own brain, doing the actual thinking yourself. Okay, that is a lot of work right there. Rows and columns, columns and rows, multiply, add. Let's kind of take a quick break here and get our heads straight. When we come back, we'll look at a different aspect of matrices. But while you're gone, as always, ponder this. Why didn't the quarter skip his math class like the nickel did, huh? Think about it.
My cell phone number.
The odds of a babysitter calling 911, 1 in 1,400. The odds of a child being diagnosed with autism, 1 in 150. To learn the signs of autism, go to autismspeaks.org.
Welcome back to Deja Vu. It's Algebra 2. I'm your host, Kevin Corby. Today we're talking about matrices, specifically matrix multiplication. Did you think about why the quarter didn't skip class with the nickel, his math class? Well, the answer is because the quarter, he had more sense. Some are better than others. Back to the math. The calculator seemed to make life a lot easier, but again, we have to know how to do it by hand, and it's really a matter of very careful record keeping. All right, so let's do another one here. I have matrix X times matrix W, and we can determine if it works. Matrix X is a 3 by 2. Matrix W is a 2 by 3. So again, the interior numbers are the same, so we know it's going to work. And once again, we're going to end up with a 3 by 3 result. So here's how we're going to do this one. We have the first row right here, and we are going to multiply the corresponding entries by the elements or the entries in the first column. So watch my fingers as I go through here. I'm going to go ahead and just call them out. We have 4 times 3 is 12, and then I have plus, so when we're done with that, first row, first column, first entries, we put a plus. Now it's the first row, first column, second entries, 7 times 1. And then I move down the first row, first column, third entries, negative 2 times 2, that's negative 4. That's our new 1, 1 position. First row, first column, that's 1, 1. Okay? I'm going to leave a little bit of space. I'm going to stick with my first row, move on to the second column. So here I go. I have first row, second column, first entries. 4 times negative 2, that's negative 8. First row, second column, second entries. 7 times 0 is plus 0. And finally, first row, second column, third entries. Negative 2 times negative 1, that's plus 2. So that was my first row. Second column, that's my new 1, 2 position in my new matrix. And we'll keep on going here. Let's see, we got first row. Let's jump to the second row, sorry. Second row, first column. So we've got 5 times 3, that's 15. 1 times 1 is 1. Negative 1 times 2 is negative 2. And then we will proceed over here. And I've noticed a mistake up here. I'm going to come back. Notice how my matrix is kind of turning out here. And I misspoke up here. But it's good because things should always work out in mathematics. So if we make a mistake, we should recognize it at the end. All right, so now I need to go with my final second row and second column. So it's 5 times negative 2. That's negative 10. And then moving over and down, 1 times 0. That's plus 0. And finally, moving over and down, second row, second column, last or third entry, negative 1 times negative 1 is plus 1. And that's it. I've systematically gone through and paired them all up. So notice I have 1, 2, 1, 2. I have a square 2 by 2 matrix. And I said up here it was a 3 by 3, and the reason is this was a 2 by 3. I had this backwards, right? Mr. Corpy, you should know better. And I do. That's why I caught it. And this is a 1, 2, 3 rows, by 2 column. So it did work because those are both 3s, but I end up with a 2 by 2. Ah, there we go. Now, we need to simplify this, so let's go ahead and do that. Now it's just arithmetic. We're just adding up all the elements in the corresponding entries. So 7 minus 4 is 3 plus 12 is 15. We get a negative 6. That's going to give us a 14, and that gives us a negative 9. All right, so in that last two examples, basically, we did matrix W times matrix X, and then we did matrix X times matrix W. And in both cases, it worked. So sometimes it works, sometimes it doesn't. But notice that they were, in fact, different matrices. So what does that mean? XY did not equal Y, WX did not equal XW. That means right here, dun dun dun, herald it. Matrix multiplication, you heard it right here, is not, I repeat, not commutative. You cannot just flip the order in which you multiply. So be very, very careful. That goes against what we know for real numbers, because 2 times 3, if I'm actually multiplying for real numbers, we know is 6, which is no different from 3 times 2. So when we're multiplying numbers, we can commute them. Multiplication itself is commutative, but matrix multiplication is, in fact, not commutative. Remember, last week we talked about matrix addition. It was commutative. But matrix multiplication is pretty special, and it's going to be very, very powerful. So if you understand how to do matrix multiplication, then on the next episode we're going to start using it to solve giant systems of equations. And knowing that it's not commutative is very, very important. Okay, let's go ahead and finish up the show now with Deja Review. So again, we learned when you can multiply matrices together. We just learned how to do it. Now here's the why. Well, we can use matrices to work with large data sets, okay, tables and tables of numbers. We're going to work with two small tables here. So when will we need to multiply two matrices together? Well, let's look at this little scenario. We have two stores, okay, they're video stores, and they're having a giant blowout sale on all their old videos, their VHS tapes and their new DVDs, okay? And they've got prices that are shown below. And this is going to be a sale that takes place at two different stores on Friday, Saturday, and Sunday. So let's look at this first table here. It's already nicely organized for us. We've got the sales prices. How much are each of these things going for? We got Video World, the store, are selling their VHS for $8.95 and their DVDs for $11.95. And then Star Movies, the other outlet, is selling their videos for $7.50, slightly less, and slightly more, $12.50 on their DVDs. Okay, so I think we clearly understand what that table gives us. This other table gives us their total sales for the 3-day event. So notice we've got Friday, Saturday, and Sunday on the columns, and we've got the videos that they're selling, VHS, on this row. So on Friday, they sold 23 videos and combined, the two stores combined. And on Saturday, they sold 48 DVDs. So that's how we would read it. Well, here's what we want to know. We want to use the sales data, which is the two columns here, to determine how much money each of the stores actually brought in from their sale on a particular day. In this case, we'll say Saturday. Okay? So let's see if we can actually create two matrices. I'm going to go ahead and call matrix S. Matrix S we're going to call the sales price matrix. So if I just list the information the way it's kind of given in the table, I can create just a numeric matrix without the headings. So there's matrix S. It's going to be a 2-row by 2 column or a 2 by 2. Let's go ahead and look at the other table and see if we can make a matrix out of it. T, I think, would be a very appropriate value for it or letter for it because it's total sales. And let's see if I write in the numbers 23, 31, 25, and then over here 40, 48, and 42. So notice I'm just kind of extracting the information straight out of the table, and all I'm doing is eliminating the rows and column headings. This is going to be a 2-row by 1, 2, 3 column. So it's a 2 by 3. All right, so can we multiply these two together? And if we can, what information will it give us, and in which order should we multiply them? Well, notice if I do S times T, the way they're kind of written, the inside numbers are 2. This has 2 columns and this has 2 rows, so it'll work. If I flip them around, I'll have a 2 by 3 times a 2 by 2, and that won't work. So the only order in which we can multiply these two is in this order, ST. Now what the heck is that going to give us? Let's go ahead and see what we have here. Notice that the resultant matrix is going to be a 2 by 3, and it's going to be whatever the original row of S represented by the 3, which was the column of T. And so we're going to get a new 2 by 3, which is going to represent 2. Let's see, the row of S was up here. What did the rows represent? That was the actual store chain. So this is going to give us our store chain. And we're going to go all the way to the third column, or the columns of what T represented. Well, what did those columns represent in T? Those were Friday, Saturday, and Sunday. So these are going to represent the days of the week. So if we look at our units, we can actually see what the meaning of the multiplication is going to be. So this will give me a 2 by 3 matrix, which will tell me the amount of sales each store had on any particular day of the week, which is exactly what I wanted. Then I can pick Saturday of the lineup by looking at the middle column. All right, now I'm going to go ahead and do this one entirely on the calculator because we're running out of time, and I think we need to see that again anyway. And when the numbers are big like this, calculator makes sense. All right, so we got to go back to our matrix edit, and we'll go to edit first, and I'll call it matrix A. And I'm going to change the size. It was a 2 by 2. So if I just change on the top, type right over what's there, 2 by 2, and we'll type in the values. 895, 8.95, enter, 11.95. Remember, we enter these in from left to right, starting on the top row, just like we'd read a book. 7.5 and 12.5. And we've got them all in there. We take a quick check, 2 by 2. Every entry looks good. We'll go back to our matrix menu, and we'll click edit. And we'll go down and we'll re-edit matrix B. Matrix B, remember, was a 2 by 3. So just typing in the new dimensions and then looking at the entries and carefully typing them in. 23, 31, 25, 40, 48, and 42. And again, a quick final check of our paper and our calculator, and everything looks good. So we'll go back to the home screen. And here's the nice thing about a calculator. I could recall A and B like I did the first time. But if it's already been typed into my calculator, I can recall that command by hitting second enter. And there it is. Even if it wasn't the last command, I can hit second enter again, and I could eventually find what I previously typed in. Now notice that if I hit enter this time, I should get a different matrix here because my A and B now have changed since the last time I've used it. It's a little bit of a time saver. Let's hit enter, and boom. There we go. Now notice we have some ellipsis points here, which means the matrix is kind of fallen off the page. So what we can do now is we can translate that into what we need on our paper. The matrix AB, or in this case it was ST, it worked, and we came up with the following matrix. We had 683.85, 672.5, 851.05, 832.5, and then down here we had 725.65 and 712.5. So again, these rows represent the stores, and it's going to be Video World and Star Movies, and then the columns represent the days of the week. So we're back to Friday, Saturday, and Sunday. Now again, we're doing it just for 2 stores on 3 days of the week. You can imagine how efficient this would be if we had many, many, many stores and we were doing it over an entire calendar. The data, it's a routine calculation, so the calculators can handle it very systematically. Now let's answer the question. What was the total sales of each store on Saturday? Well, that information is found in the second column. And so here we go. The first store, which was Video World, sold $851 and a nickel to spare on Saturday, and its competitor, Star Movies, did not quite as well, $832.50 on that particular Saturday. Hey, speaking of videos and DVDs, if you're watching today's program and you like what you see, or you're watching today's program and you don't like what you see, but you want a copy of today's show, or maybe you're not watching the show, but you want to get a copy of the show, or you haven't seen some of the other shows, but you heard they were good, you can order a copy of today's show or any episode from Deja Vu, It's Algebra 2, or any show that's been on Channel 98. You can order your very own copy. Just log on to the district website, click on the Channel 98 link, and send us an email, and we'll be happy to give you the information to have your very own copy of today's show. Watch it anytime you want. Doesn't have to be on TV at the time. They also make great stocking stuffers. Christmas is around the corner. Now you want to write that down and you want to get out a big highlighter and highlight that. They make great stocking stuffers. Order your own DVD. Now, plugging the DVD kind of made us run out of time. We're out of time with today's show. Hope you learned a lot about matrices. We're going to do them again next week. So practice, 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 and we'll be able to hit the ground running next time. And until then, I'm Kevin Corpy reminding you, of course, to do your homework.